Okay, today we will talking about the numerical method for solving ordinary differential equation that we will first mention to the first types of problems, that is the initial value problems. Okay. Before we start, we have a little bit review for the definition for differential equation. A differential equation is the mathematical equation that we have an unknown function of one or several variables that's related to the value of the function itself and its derivative of various order. So what does it mean? It means that the differential equation is have some term that is has the term of differentiation and derivative. Okay, so this is the example of the differential equation that it has the the value uh, for an unknown that is in term of the the function and its derivative. So if the equation has the derivative term or the differentiation term, so we call the differential equation. Okay, and we can classify the differential equation into two types. Okay, first is ordinary differential equation, that is a differential equation in which the unknown function, okay, is functions of a single independent variable. Okay, we have just only one independent variable. We have only one independent variable. But for the case that if we have more than one, okay, more than one independent variables, this is multiple independent variables. Okay, so we call the partial differential equation. It means it is a PDE. Okay, for that case, if we have more than one independent variables, so we will use the partial derivative symbol. Okay, this is just the example for the differential equation. The first one, we have just only one independent variable, that is just only variable x. Okay, you see that we have just only variable x, and we use the derivative symbol, that is dy by the x and d2y by the x to represent the second derivative. Okay, but for the second equation, we have two independent variables, that is x and y. Okay, so then we will use the symbol of we use the partial derivative symbol instead, that is this symbol. This is we call the partial derivative symbol. Okay, so this term we call the second partial derivative of u with respect to x and y. Okay, so for this case, we have two independent variables, so then it is a PDE, that is partial differential equation. And the last one, for the last case, this is we have just only one independent variables, that is the time. Okay, so for this case, we have just only one independent variable. So then the derivative term we represent by d by dt. Okay, so we call it like the ordinary differential equations, or ODE. Okay, and this is the definition. Okay, and for the order of differential equation, the order of the differential of a differential equations means that the number of the highest derivative in a differential equation. Okay, so if the differential equations of order 1, we call the first order differential equation. So if the highest derivative in that equation is 2, we will call second order differential equation. And if it's become 3, we call third order, fourth order, okay, and so on. But in engineering application, the highest order of our differential equation in engineering application normally it not exceeds fourth order. Okay. So for the example, if we mention to this equation, you see that this is the differential equation because we have the term of derivative over here. Okay, and the highest derivative of this equation is the second order derivative. Okay, so in this example, this equation we call the second order differential equation. And then if we consider this example, you will see that the first one, we have just only one independent variable. Okay, so then it is ordinary differential equation. And for this case, we will focus on the order, the highest order of derivative. Okay, so for this equation, we found that we have the highest order of order 3. Okay, so then we call this is the third order. Okay, and this is the ODE. Okay, so then the first equation is the third order ordinary differential equation. Okay, and for the second one, you see that we have two independent variables like this. Okay, and the highest order of this equation is the second order. So we call this equation as the second order partial differential equation. Okay, because it has two independent variables here. Okay, are you all right? So this is just a little bit review for the classification of the type of the differential equation. That's just we have to know. And next we move to the degree of a differential equation. The degree of the differential equation is the power of the highest order derivative in the equation. Okay, so if we consider the first one, we will see that the first equation is the ODE, right? Because we have just only one independent variable. Okay, so this is the ordinary differential equation. And the highest order is the third order. Okay, and the degree and the highest power of the highest order derivative, okay, is equal to 2. So we call this equation as the third order ordinary differential equation of degree 2. Okay, of degree 2. Okay, we will not mention this number. Okay, this number that it is degree 3, but it is the power of the second order derivative. That is not the highest one. The highest for this equation is the third order. So degree is represent the power of the highest order derivative in the equation. So this is just the third order differential equation of degree 2. Okay. So for the second one, we have the one independent variable. So then it is ordinary differential equation. And it is the second order. Okay. The degree of this equation is degree 3. Okay. So that is the definition for the differential equation. And then we will consider the type of differential equation in another point of view, that is about the linear and linear differential equations and nonlinear differential equation. For linear differential equation, it means that For example, for the second order differential equation, we will mention that the linear equation is maybe right in this form for the second order. And for the third order, it's just like in the same manner. You will see that we have the coefficient function. Coefficient function represented by A, B, C. Okay. And the right hand side, okay, is D. That is another function also. But we will focus on A, B, and C. Just really A, B, and C. That is a coefficient function. We focus on these terms, A, B, and C. Okay, this is just for the example for the second order differential equation. If we have the third order, fourth order, and fifth order, or so on, we may have more than three. Okay, coefficient function. So if this coefficient function A, B, C are constant, or the function of independent variable, for this case, it is the function of x only. It is not function of y. Okay. If the coefficient function A, B, and C are constant or are just only function of x, okay, we will call this type of equation is the linear differential equation. But if the coefficients function A, B, and C are function of y. Y means that it is the dependent variable. So if A, B, and C are function of y, it is not linear differential equation. It's become the nonlinear differential equation. That is, in general, this case for the nonlinear differential equation, exact solution, or the solution that we can formulate the exact formula for the solution, it maybe not exist for that case, or it's maybe very complicated for that. Okay. So for this case, if we consider for the example of the problem of single swinging pendulum, okay, for the pendulum oscillation, if we derive the equation of motions of the single pendulum like here, like this picture, we can form the second order ordinary differential equation like this equation. And you will see that from this equation, we have, it is the, for this equation is what? This is the second order ordinary differential equation. Okay, and you see that we have the term of sine theta. Okay, theta is the dependent variable. Okay, and it is in the function of sine. So then sine function is the nonlinear function, and it is a nonlinear function of the dependent variable. So then these equations become the second order nonlinear ordinary differential equation. Okay, that is maybe not convenient to solve analytically. Okay, so in order to solve this equation, we may write this equation, simplify this equation, or reduce the order of differential equation to be just the order one, the first order. Okay, in order to simplify this, we may set up d theta by dt to be another function that is we define it to be beta. For this case, we define d theta by dt become the function beta. And then what does it mean? It means that this equation, the first equation here, this equation can be simplified, reduced from the second order to be the first order. That is changed to be d beta by dt equal to minus g over L sine theta. Okay. But we have we can reduce the order. We can reduce the order from the second order to become the first order. But instead that we have to change the second order differential equation, just only one equation, to be the first order differential equation, but it's composed of two equations to solve. That is, it means that we have to solve the system of first order nonlinear differential equation instead. So that is the technique to find a solution for the case that we have the higher order differential equation. We may reduce the order of differential equation by this technique. Okay, why we have to do like this? Because for this course, we will mention to apply the numerical method for solving the first order differential equation, that we can expand this technique for the case that for solve the nonlinear, for solve the problem of the higher order differential equation, because we can simplify, we can reduce the order of differential equation to be the first one, be the first order. But by reduce the order, we will solve the system of the first order differential equation instead for that case. So if we consider here, we will see that for the second equation, this is the first order right now. Beta is the independent variable. Okay, and it's the independent variable is t. Okay, G and L is a constant. Okay, but psi theta, you see that actually beta is a function of theta. Okay, so then theta is a function of time. Okay, so then this equation is become nonlinear. Okay, because it is not psi t, it is psi theta. If it's psi t, this equation become the linear case, but it is not, it is psi theta. Theta is a function of t. It is the independent variable. Sorry, it is a dependent variable. So then we will see that this system become the system of nonlinear differential equation. But if we simplify psi theta, okay, by just consider just only the small angle oscillation, we can assume that for the case of small angle, okay, psi theta is close to theta, and after that we change, we approximate psi theta become theta instead. So now the equation that is actually it is the nonlinear equation according to the psi theta term. So then now we will simplify psi theta to be theta, and this equation become the linear equation instead. Okay, because the psi term is approximate to be the theta, just only theta. Okay, so according to this equation that we already simplified, we can solve for the exact solution right now by using the analytical technique that we have learned in mathematics 3 to solve the second order differential equation. We obtain the exact solution like here, that is theta at any time equal to theta 0, that is the initial condition. Okay, cosine square root of G over L times T. Okay, T is the independent variable. So now we can find angle theta, the magnitude of angle theta at any time T by using this formula, and it is the exact solution. And we know that for this case, okay, we have two conditions to find the exact position, that is theta 0, okay, theta 0 is the initial condition. Okay, so for this case, when we substitute time equal to 0, it had to be theta 0. And also the second condition, that is maybe the term of angular velocity. For this case, that is d theta by dt, that is t equal to 0, and angular velocity is become 0 because it's maybe released from rest. In that case, okay. So this is just for the small angle. We have the exact solution that is easy to find. But for the case of large angle of oscillation, it may be hard to solve analytically according to the nonlinear term of this. Okay. So how can we do? This course, this chapter is we will focus on the solving ordinary differential equation in this form. That is we will focus on this form dy by dx equal to fxy. Okay, if we back to here, okay, it is should be right in this form, right? It is d theta by dt equal to beta. So it is same type. Okay, same type of the equation, same form. That is the form of dy by dx equal to fxy. So for this first equation, y is mean theta. Okay, x is represented by t. Okay, and fxy now is beta. And for the second one, y is beta, dy by dx, and x is become t. Okay, and fxy is equal to minus g over l sine theta. Okay. So we will focus on the equation in this form. For example, if we have the differential equation here, and we have fxy is represented by the polynomial function, the second order polynomial function, like this. So then we have the equation to be dy by dx equal to 3x squared minus 2x plus 1. And fxy here is the second degree polynomial, like this. So for this case is because on the right hand side it's just only the polynomial function, so then it's very easy to solve. We can find the solution by just only direct integration. Okay, we change the x to be the right hand side and integrate both sides. We get y equal to this equation with the additional constant c. Okay, so in order to solve the constant c, we require the initial condition. For the initial condition, is mean that at x equal to 0, okay, when x equal to 0, this is the initial value, okay, and y is become 2. This condition, the problem had to be defined. Okay, according to this condition, we can determine for c. Okay, the constant c is become 2. And now we have the exact solution right here. Okay, oh sorry. Oh yes, okay. This is the exact solution. Okay, that is y equal to x power 3 minus x power 2 plus x plus 2. This is the exact solution for of this differential equation. That is not easy to understand, right? Okay, because it's just the polynomial function. And if the equation is not just like the simple case like that, it is not the polynomial function, how can we do? In this time, okay, we will study 4 methods. We will study 4 methods. that is the Euler method, Huon method, modify Euler. Okay, that is for today. We will focus these three methods first. We will focus on these three methods. And after that, on Monday, we will move to Lunge-Kutta method. But actually, I would like to focus on these three methods first. It is easy to understand if you understand these three methods. Okay, for the Lunge-Kutta method, that is the good one, and we will just use for engineering application. It is recommended to use just only Lunge-Kutta method. For Euler, Huon and modify Euler, it is easy to understand and make us understand for the concept, but it is not good enough to determine the result. Okay, so for the engineering application, in order to solve initial value problems, okay, to solve the differential equation of the first order, we normally use Lunge-Kutta method. Okay. So before we start, we should understand what is type of initial value problem. Okay. So for the case of we have the system of differential equation like this. We have the system of equation. For this case, it's just only two equations. That is, we have dy by dt equal to f1 and dy2 by dt equal to f2. So according to this, after we solve this equation, okay, we should obtain two constants. Okay, in order to find those two constants, we require two conditions. Okay, we require two conditions. And if that two conditions are located at the same point, for example, in this case, we have at time equal to 0. Okay, time is the independent variable, right? Okay, so then when at the same time equal to 0, okay, we have two conditions. That is y1 equal to 0. Okay, y1 is not equal to 0. Y1 is equal to y at time equal to 0. Okay, and y2 is equal to y2 at time equal to 0. Okay, so for this case, okay, we have two conditions that's located at the same point at the same time. Okay, we will call the initial condition. Okay, these are the initial value because it's the condition that we know are specified at the same point. Okay, if all conditions are specified at the same value of the independent variable, we call this type of problem as the initial value problem. Okay, but for today, we just focus, and for today and for this course, we focus just only one equation. So then what it means? It means that we have just only one condition. So normally, for the case that we have just only one condition, it's always become the initial value problem. Okay, because we not require the second one. You're right. Okay, but for the case that we have to solve more than one equation, it's maybe two equations or the higher order differential equation, we require two conditions to solve for the constant. Okay, if conditions are at the same point, we call initial value problem. And if the condition is not specified at the same point of independent variable, we will call it like the boundary condition, boundary value problems instead. Okay, that's this is the last topic that we will mention too. Okay, and we will not focus today. Today we will just only focus to the initial value problem. Okay, we repeat that. We we'll focus on just only the differential equation in this that is right in this form, that is dy by dx equal to f(x,y). Okay, dy by dx equal to f(x,y). So according to this, so it means that according to the definitions of dy by dx, it can be approximate to be delta y by delta x, like this term. Okay, so for this case, when we write dy by dx approximate to be this term, what does it mean? It means that for dy, we approximate to be delta y, that is yi plus 1 minus yi. Okay, and the x is xi plus 1 minus xi, that is h. We define it to be h, that is different in x, and is step side. Okay, step side, that is different in x. Okay, after we substitute this equation, we can predict for the next value of y. Okay, from the initial condition, yi actually is the initial condition that we should know from the problem, that is defined from the problem. This is the initial condition. If we know the initial condition, okay, we can approximate the next value of y by the initial slope, that is f(x,y). Okay, according to the equation here, you see that dy by dx equal to f(x,y), and we know from the calculus that dy by dx is the slope of the function y. Okay, so it means that f(x,y) is the slope of the function y at that specified point. Okay, and for the Euler method, we approximate the next value of y by using the initial slope. What does it mean? It is the slope at the initial point. It is a slope at the initial point. That is this point. Okay, and we predict the slope at this initial point. We predict this slope. Okay, we use the slope at the initial point for predict the value of y in next step. Okay, and you will see that it may give us a lot of error here. Okay, different from the exact solution that we can derive. Okay, for that case, and it is just the general concept. Okay, that is defined as the Euler method to approximate another value of y. Okay, let's take a look at this example. Okay, we have this differential equation. From this differential equation, we can derive for the exact solution by analytical technique like this, and we found out the exact solution for this problem is become y equal to e power psi x. Okay, and then if we apply the Euler method for solving this equation, you see that this is the in the form of dy by dx equal to f(x,y). So for this case, f(x,y) is y cosine x. Okay, and after we write it in this form by using the Euler method. Okay, so yi plus 1, we would like to predict yi plus 1. It's become yi plus yi cosine xi divided times h, like this. Okay, and we know the initial condition from the problem that when x equal to 0, y equal to 1. Okay, And for this problem, we will use the increment step h equal to 1. So it means that from the initial value, as we already know, okay, substitute into the equation, and we will get y1. y1 from the Euler method is equal to 2. In comparison with the exact solution, the exact solution here is e power sine 1. Okay. So for this case, we obtain that the error from this process, the error according to the Euler process is equal to 0.31978. Okay. If we comparison with e power sine 1, okay, so then we can find the percent error instead of the error. So when we apply the Euler method, okay, you will see that we may create a table like this. That is for x, the step size is equal to 1. So then when we would like to determine the function of y at the specified point x equal to 1, 2, and 3. Okay, we would like to find at the final position, that is 3. Okay, and this is the initial value. Okay, this is the initial condition that's given by the problem. This is given by the problem. But I would like you to mention that, okay, when you going to work and you have to make a decision by yourself that the initial condition should be what? It's maybe not quite the same, that y should be equal to 1 for all time. So for it depends on the problem also. So but for this case, we apply s equal to 1 for Euler. Okay. So after we solve, okay, we use the 1 as the initial condition. Use this, the first row, as the initial condition that's given from the problem. Okay, after that, we apply the Euler method by substitute x equal to 0 and y equal to 1 into this equation. So for yi is equal to 1, right? Okay, plus yi, that is equal to 1. Cosine x, okay, x is equal to 0 now. Okay, and substitute x equal to 0 into cosine function, and we get equal to 1. And substitute h, this is the last one. And after that, we can mean for y1 equal to 2. Okay. And okay, if we, the previous time, we use the initial value problem to determine the step, the second step, that is at x equal to 1. And after we know the value of x when x equal to 1, when s is equal to 1 now, when s is equal to 1, and then we will have y equal to 2. And now we have to believe that this value should be the correct one, and we will change it to be the initial condition for next step. Okay, so for this case, when we determine for y at x equal to 2, so we have to apply, okay, the condition that when x equal to 1, that is the previous step. Okay, when x equal to 1, y become 2, and s is equal to 1. Okay, yi is equal to 2. So then we can determine for y at x equal to 2 over here. Okay, that is very easy to understand. And after that, we move on the final step here. Okay. So when we compare with the exact solution, you see that the Euler method is not good enough. It has a lot of error. So, but it is an easy one that gives us the idea for solving the initial value problem. Is just based on the basic idea like this. Okay. So for the case that when we apply, we subdivide h to be smaller value. That is we use s, use the step size, reduce the step size to be 0.5. Okay, we do the same procedure. We find out the solution is become here. And in the same manner, if we subdivide h to be the smaller value, that is maybe 0.25. Okay, we can determine the value for each point like this. Okay, and then if we compare it with the exact solution, you will see that when we use the smaller h value, that is we use the small step size, the solution is in comparison with the exact solution, it is better than the solution that approximate the value of h is not small enough. Okay, but you will see that the solution that obtained from the Euler method comparison with the exact solution, even though we use h to be the smaller value already, okay, but the error is maybe not acceptable. It's maybe not acceptable right now. But you see that for the Euler method, it's very easy to understand, right? Okay, and according to this, if we compare the error of the Euler method, see that if we just plot just only h equal to 1, so the error have a lot. Okay, but for the case that when we increase, when we reduce the size of the step size, okay, is give us better solution. But actually, if we would like to focus on the more precise solution, it's a more correct solution, the Euler method is maybe not good enough because it has a limitation. And you will see that the error will increase for each step that is far from the initial value. Okay, so then we need to improve this method to be another one that is maybe give us better solution. Okay, I will stop the clip right now. Okay, for the case that we discussed about the overview about the Euler method, that is the basic, very basic concept for solving the for set up the numerical method for solving the differential equation in case of initial value problem. Okay,